but just as an example. Then, okay, then we'll look at the difference densities, attachment, difference densities up here, attachment densities down here, detachment densities down here. Also, those 4 densities look exactly the same for those 4 states. And this kind of takes us to the next step. So if all these analysis methods fail, what do we do? And this allows me to go back to a transition density matrix, which in many cases is my favorite quantity for looking at excited states. So I already actually explained this. And the important point here is that the ground state and the excited state are connected in a one matrix element. That's why the transition density can tell us things that we wouldn't find from the difference density. So we do that. We compute the transition density, which is the diagonal of the transition density matrix, kind of where the hole and the electron at the same point in space. Suddenly we do that, and we find the difference. The minus states have transition densities on the bonds. The plus states have transition densities on the atoms. And then, yeah, you can think about kind of this as a strong transition moment, because the transition moment is just the thing pointing from the red blob to the blue blob. But then kind of we can think about the energies. And when you look at this, then, for example, the question is about, do the singlet and triplet transition densities look almost the same for the minus, but the plus transition densities don't look almost the same because you have all these extra sigma blobs here. So that's kind of one of the questions you may ask yourself if you find this. And to do this, we should look at the theory. If you think about the CS singles excitations energies, you have those 3 terms. You have kind of the weighted orbital energy difference. Then you have this term that comes from, the Coulomb or Hartree potential in Hartree-Fock. And you have this term which comes from the exchange potential. But the interesting thing is that in the electron hole picture, this term here is called exchange repulsion or exchange splitting. And this term here is called Coulomb attraction. So kind of these terms suddenly change the name. That's just something to keep in mind here. And then you could think about this one is only for singlets. This one is for singlets and triplets. And this one is into the DFT. And this one is kind of the non-local exchange bit. So yeah, I'll hurry up. But let's say just to kind of understand this first term, that transition density self-repulsion, we separate this. We do this integral first, which is the electrostatic potential induced by the transition density. So now we have our transition densities here, which is this term, and the electrostatic potential induced by the transition density down here. And then just kind of to give you a quick idea, then we can see the minus state only has a very little bit of electrostatic potential because this thing cancels out. The plus state has a lot of electrostatic potential. And that's why this term is going to be bigger for the plus state. And then, I mean, if you look into more detail, then you can see kind of that the singlet uses these little blobs to reduce the exchange repulsion compared to the triplet, if you want to go into more detail here. So, and then, yeah, just kind of to quickly go, the other thing is a true non-local two-body term, which is a bit harder to visualize. But here we're computing conditional electron density. So we're fixing one quasi-particle on one of the atoms and seeing the distribution. So basically, for example, we might fix the hole on this atom, and then we see for the minus state, the conditional electron density escapes from the hole. For the plus state, the conditional electron density moves to the hole. Same here, and then we also find this for the different irreps that kind of the covalent states have reduced electron hole overlap, and the ionic plus have increased the electron hole overlap. So kind of we get a consistent picture here. All righty, then just to talk a few minutes about the implementation. So we want to have a flexible wave function analysis toolbox where we can have different quantities, as I said, the transition densities, but also difference densities. Then we want to analyze different things. So it's just pictures, population analysis, fragment-based analysis, and then these more sophisticated things I talked about. And we want to support many different types of computational methods. So here the point is that there's not a one-size-fits-all solution, but the analysis needs to be tailored to the problem at hand. And now, kind of how can we create a framework that gives us this flexibility? And there are actually two tools. One is called Theodore, Theoretical Density Orbital Relaxation and Exciton Analysis, which is an open source program for post-processing quantum chemistry programs. This is written in Python, where kind of the nice thing is easy to write new interfaces. So that's why so many programs are interfaced. There's a flexible interface for the user. The downside is that the maintenance is difficult because, different programs might change the interface, and also not all features are available in all the programs. So it's just kind of a bit of a mess to keep up all these interfaces. Then the second thing we have is a wave function analysis library, libwfa, that's integrated and shipped with specific programs. In this case, it's with QChem, OpenMorcus, and there's also a C4 interface. So this is written in C++. The advantage of doing it in an integrated fashion is that the maintenance is more easy because it just is in a standard testing system of OpenMorcus and QChem, and you can also have a bit more possibility to play around because you can dig deeper into the quantum chemistry program. The downside is, first, it's written in C++. I don't get C++, but it was written that way, and so then ultimately it's more work to write a new interface because it's a more rigorous framework, and then you're tied to specific quantum chemistry codes. So for example, of course, one of the things is that QChem is commercial, so then I have all these features, but only paying users of QChem can use it. So that's the downside of this type of development model. All right, just to quickly go through the conclusion. So I hope I showed you that we have this wave function analysis toolbox, where one thing is that we can just press a button, assign the state character automatically. This works for transition metal complexes, but also for many other types of systems. The other idea is that we want to gain deeper physical insight. We talked about the valence bond picture. We also talked a lot about electrons in conjugated polymers. Just before I close, if you're interested in any of this, there's two new papers that came out in 2020. So there's a JChem-Phys paper for just kind of the first point, just press a button to automate things. And if you're interested more in the chemical theory, then you could go to this PCCP paper down here. And then I just want to acknowledge some of the people that were involved in the work that I'm doing here. And just to show you, in case you've never heard of Loughborough, it's right here in the center of England between Leicester and Nottingham. Okay, thank you very much.
Thank you. Thank you for a very nice talk. I think Professor Mario Barbati has a question, please.
Yes, thank you.
Yeah.
Fantastic talk, Felix. Thank you very much. As usual, I learned a lot listening to you. As you know, my group is a heavy user of Theodore, and right now we're coming to a limitation. That's the analysis of double excited and multiple excited states. And there it seems to be quite a hard problem because it goes beyond the formulation of this density matrix, transitional density matrix. Do you see how the theory can be expanded to deal with high order excitations?
So let's say one thing, that difference density is a bit more robust. So let's say you see changes in the density and in the difference density matrix, even if it doesn't work for the one particle transition density matrix. Otherwise, sure, I think one can extend this whole thing to the two-particle transition density matrix. It's just, that's it, then it's more work in terms of kind of coding this efficiently. And I think one would really have to think about the physics. So for a double excitation, you know, you have two holes and two electrons that are correlated in some non-trivial ways. So I think first you'd have to understand the physics, and then you can start coding it. But it's definitely possible, but it's not something like to do in an afternoon.
Okay, thank you.
Okay, and Dr. Sebastian Mai, also question, please.
Hi, Felix. Also from me, thank you very much for your talk. It was very nice. Especially I'm intrigued by this new real space analysis of the transition density that you were showing for the naphthalene. Do you already have plans for quantifying that to go again away from blobs of colors?
For the electrostatic potentials, you mean?
Yes, these conditional densities and the electrostatic potentials and so on.
Yeah, so let's say for the conditional densities, actually, let's say you have this term, or let's say this term, and this is actually quantified. So here I'm giving you the numbers for the transition density self-repulsion. I mean, in this case, this is computed in a semi-numerical way, but of course that's easy to compute. And I mean, the other term is also easy to compute. I mean, those are both, formally speaking, those are like the Coulomb and exchange matrices from Hartree-Fock. So you can reuse these engines, and then you can get numbers for these terms as well.
You're proposing an energy decomposition for DDDFT and CIS schemes, essentially.
Yeah, sure. I mean, so I haven't coded this up, but in principle, of course, you can get those three terms explicitly. So then you have the orbital contribution, the exchange, the Coulomb contribution, and then if it's an, let's say, a correlated method, then you have the extra correlation things. So in principle, it's not difficult. And I mean, of course, these terms are computed by whatever quantum chemistry code you use. These terms are already computed. It's just that no one prints out individual contributions.
Okay, great, thank you.
Okay. Well, time is over, but let's accept the one. Would you, so Professor Emmanuel Fromark?
Yes,
yeah, please.
Yeah, thank you very much. Just a quick question. So Felix, congratulations, really nice. I have a question. It's not directly related, but I think you have the tools for that. Did you think about computing like Dyson orbitals? I mean, if you're interested in ionization or affinities, it seems to me that you have almost the technology for doing that, and people are very interested in this, because with your transition density matrices, somehow you would have access to intensities regarding like ionization, for example. So you probably would have to work a little bit on your code, but is this something you considered, or?
I've looked at Dyson orbitals. I guess the different thing is, I mean, the Dyson orbital fits into the same idea. I mean, there's also a paper by Zederbaum, for example. The transition density matrix has two operators here. And if you just have the annihilation operator, then you have the Dyson orbital.
Yeah, because you need to construct the n-1 ground state, for example. So then you would have a linear combination of your like CQ and AQ, for example, something like that. But, because it seems to me you have the technology for this. So I think it would be interesting. Then you could compute maybe Dyson orbitals at the KSSF level, or I don't know if anyone has looked at that before. But
I mean, let's say kind of these tools already take things that are already there, but I mean, that's something else we did in Vienna, actually, is computing wave function overlaps and Dyson orbitals. So, I mean, I can show you the code. So that's in the Shark package. We can compute Dyson orbitals for arbitrary wave functions for KSSF, for MRCI. I mean, I can show you the code. So that's available on GitHub and can be used.
Okay, thanks. Okay, thank you very much.
Okay, now the time is a bit delayed, so let's thank Professor Felix Plasser again